Okay, so this video is about water potential. So we just talked about osmosis and facilitated diffusion, and this is a review about the equations for water potential and how to use those. Remember, water potential is basically the potential for water to do work. So like I talked about in the osmosis video, when water is dissolving a salt, it's going to be occupied and not available to do work. And so when you have water potential, it's just how much water is available to actually do work. How high is the water concentration? So if we look at our equations, water potential, we use this little Triton sign called psi is equal to the solute potential plus the pressure potential. And in an open container, the pressure potential is 0. And so if they don't give you a pressure potential in a problem, then just assume the pressure potential is 0 if you're probably like in an open container. And a solute potential is actually talking about how much solute is dissolved in the water. Hold on one second. Sorry, I'm currently getting a makeover while I make this video. Okay, sorry. So here we have a situation where they could ask what is the water potential if, let's say that the solute potential was -3 and the pressure potential was +2. Then you would just add these together, -3 plus 2, your overall, let's say this one would be pressure and this one would be solute. So then you could just find your overall water potential, meaning this variable would be -3 plus 2, and your answer would be -1. So we would say that our water potential is -1. So let's say the water potential of the cell here is -1. And let's say you're given the information in the problem that the water potential of the solution is -5. Remember that water always goes towards the more negative number. And again, you can think of it again as like a salt sucks. So here it has more salt, more solute than this one does, because the more negative the number, the higher the salt concentration is. And so our direction of water flow is going to go in the direction of the bigger negative number. You'll never really have a positive number unless there's like a really ridiculous pressure potential. So here, water is going to go towards the more negative direction, and so it's going to leave the cell. So we would say that it's in a hypertonic solution. Our cell is shrinking. Water is going to exit the cell, and it's going to go in the direction of the higher negative number. So the more negative, technically the smaller number. Remember that the water potential of pure water is 0 because it has no solute in it, and then it also has no pressure if it's in an open container. And so this is pure water. So anytime you add salt to it, it's just going to get more and more negative. So the more negative number, the more salty it is. And remember, salt sucks in the direction. So you're always going to move your water in the direction of the higher negative number. So let's use the bottom equation, because usually people have no problem with the first equation. It's when you have to factor in the bottom equation. Sorry, hold on one second. Okay, so we're going to look at another example. My really sophisticated platform here is Paint, so sorry, it took a while to erase. Okay, so let's say if we need to use this equation. So let's say that we're not given the actual solute potential, but we are given the concentration. So let's say that the concentration, meaning the molar concentration, is 0.5 molar, and we're looking at NaCl. So let's say that they give us that there's a concentration of 0.5 molar NaCl that the cell is surrounded in, and we need to actually, and let's say that they tell us the pressure potential is 1. So the solution surrounding the cell is 0.5 molar, and then that's sodium chloride, and then the pressure potential is 1. So we're not given enough information to actually plug it in. to this equation up here, we actually have to solve to determine what the solute potential is using this. So our equation would look like the water potential equals, instead of solute potential, we would insert the equation negative ICRT, and then we would add the pressure potential, which is 1. Here, we would need to know the ionization constant. We need to know the concentration. R is a constant that will be found on the actual formula sheet that you're given. And then here, they would have to provide you with the temperature somewhere. So let's just say the temperature is 22 degrees Celsius. This temperature needs to be in Kelvin, and this is a constant. Okay, so what do we do with this information? So we actually need to plug this stuff in. So if the solute potential, sorry, I shouldn't have done that. So this whole thing represents the solute potential. And then this was our pressure potential. And then added together will give us our water potential. So we were told that our concentration is 0.5 molar. We need to determine the ionization constant. This is a constant found on your review sheet or your formula sheet that you're given, and we were given the temperature in Celsius, so we need to convert it to Kelvin. So for my solute potential, it is negative. The ionization constant is how many particles are dissolved in water. So for NaCl, when I put this in water, how many particles form? Well, I have 1 particle of sodium and 1 particle of chloride. So my ionization constant for NaCl would be 2. The concentration was given to you at 0.5, and again, that's a molarity. R is 0.0831, and the T is going to be 22 plus 273 to make it Kelvin, so that gives me 295. So I'm going to pause this so that I can do the math. But when I multiply all this together, it's going to give me my solute potential to be, drum roll, hold on. Okay, so the number I got for the solute potential, and don't forget your negative sign in the front, is negative 24.5. And so for our solute potential, the answer is negative 24.5. Remember, for our water potential, if this is negative 24.5, we're going to add the pressure potential, which was given to us in the problem over here, to be 1. And so our actual water potential of the solution is negative 23.5. So if that is the water potential of the solution is negative 23.5, and let's say that given to you in the problem, the pressure potential or the water potential of the cell was like negative 5, then you could predict the direction of the water flow would be from the smaller negative number to the larger negative number, because this is much more highly concentrated, and so water would go towards the larger negative number, so it would exit the cell. Okay, so that would be how you apply this equation. I'm going to do one more with you guys where the ionization constant is different, because that's a lot of things, that's something that trips up people. Remember, it's how many particles does it dissociate to in water. So when these ions get in water, they're going to be broken apart, and while water dissolves them. So NaCl, KCl, anything that is an ionic compound will break out into the individual ions. So our ionization constant is 2 here. I'm going to do one with sucrose where you'll see that there is a different ionization constant. Okay, so let's say I have a situation that the solution has a water potential of negative, I don't know, 12. And we need to figure out what the water potential is inside the cell. So we need water potential equals the solute potential plus the pressure potential. Let's say that the concentration of this is Let's do it at 1.2 molar. And we need to actually determine what the water potential is. So if we're just given a molarity, that means we need to use the equation solute potential equals negative ICRT. Let's say this is at 15 degrees Celsius. And we'll say that our pressure potential is not given. In the problem. So we're going to assume that that is 0. Let's say we remember from our formula sheet that this is 0.0831, and I need to know my ionization constant. Well, to know the ionization constant, we need to know what is the concentration of. So the last one, our concentration was of NaCl. This one, I'm going to say it's of sucrose. So these are the two they like to use, sucrose or NaCl. So here, if it's 1.2 molar of sucrose, sucrose does not break apart in water. Water surrounds sucrose and dissolves it using the functional groups that are in the sugar, but that does not actually break it down into individual carbon molecules that are in the sugar. So sucrose is going to have an ionization constant of I equals 1. Because it does not break down, it remains one whole molecule. So if I'm going to find my solute potential, it's going to be negative ICRT, so negative 1 times 1.2, which is my molarity, times 0.0831, which is my R, times, I said the temperature was 15, and then I'm going to add 15 plus 273. So when we do all that, it will be, I'm just going to type it in my calculator, sorry, drum roll. 1 times 1.2 times 0.0831 times 288. So my answer is, for my solute potential, is negative 28.7. So to get my water potential, it would be negative 28.7 plus my pressure potential, which, since it was not given, I'm going to assume is 0. And so my water potential is equal to the solute potential in this case, which is negative 28.7. So if I go up here, I'm going to say, well, my water potential of my solution was given in the problem to be negative 12. My water potential of the cell I had to solve for using this equation, which is what we just did. So my water potential of the cell was negative 28.7. Water is going to go in the direction of the higher negative number, so water is going to go into the cell. That means we are in a hypotonic solution, causing the cell to swell like a hippo. Salt is higher inside the cell, so water is going to move where there's a larger negative number. Salt's going to suck, and the cell would swell, expand, potentially bursting. So that is water potential. So sorry, I know it's not the best platform for writing, and it's kind of messy, but hopefully that helps.